Welcome back, guys. We're going to talk about the central limit theorem for sums. We just got done going over 7.1 and now we're going to start at 7.2. So this is going to be basically the same, but now it's going to be in regards to sums versus means. So if you'll go to your packet, this is section 7.2. Okay. All right, this is very similar to last time. Remember, this is a free textbook. So this is mu sub x and this is sigma sub x. It's just a typo. They're not supposed to be multiplied. They're just labels, okay? All right, so as we move into this, the central limit theorem says that it's still basically the same thing, that when we are looking for sums, that it approximates the normal distribution. Remember, it doesn't matter what the underlying distribution is, whether it's binomial or uniform or anything like that. If we have a large enough sample size and it's done with replacement, then we can use the central limit theorem to approximate, the normal curve. So the z-score can be found here, and this is how we do the mean for the sum of x and the standard deviation for sum of x. So if you'll hold on just a sec, I'll get this fixed. Alright, so this is a review of what we did in the last video. So we're talking about the central limit theorem as it regards into means. We use x bar to talk about that being the mean. So when we're doing the mean of the means, it's going to be the same as the mean of the regular one. And then when we do the standard deviation for the means, it's the standard deviation divided by the square root of n. And remember that n is the sample size. And we want our sample size to be at least 30. Okay, so this is what we did in the last video, and this is what it's going to be for sums. I just wanted to show you these side by side, so they're very similar. All right, so for this is a capital sigma. We mean that as sums when we add things together. So the sum of x. And to do the mean for this, it's not just the exact same as it was over here. We have to multiply it by the sample size. Okay. And then for the standard deviation, instead of dividing by the square root of n, we now multiply by the square root of n. Other than that, everything else stays pretty much the same. All right, so we're going to walk through example 7.5. This is on page 402 in your packet. So page 402, example 7.5. So an unknown distribution has a mean of 90 and a standard deviation of 15. The sample size is 80. And it's drawn randomly from the population. So we're asked to find the probability that the sum of the 80 values is more than 7,500, and then we want to find the sum that is 1.5 standard deviations above the mean of the sums. Okay, so let's start on part A. So first of all, it doesn't matter what kind of distribution this comes from. If we have a large enough sample size, which we do, we can use the central limit theorem to use the normal curve to help us figure out the probability that the sum of the values is more than 7,500. All right, so now we've got this pulled up to our normal CDF, and I have my lower limit as 7,500 because we're looking for the probability that it's more than 7,500. So I've made my upper limit 1 times 10 to the 99th power. And then for our mean, now that we know that this is sums, the mean is going to be the square root of, the mean is n times the mu, so it's going to be 80 times 90, and that the standard deviation is the square root of n times the standard deviation. So that's going to be the square root of 80 times the standard deviation, 15. So then when we go through and do this, we paste that. And our probability that the sum of the 80 values is more than 7,500 is 0.0127. All right, so once again, this is what it would look like in the bell curve. So we're looking for the probability that it's more than 7,500. So that's why we're doing greater than 7,500, and we ended up with the probability being 0.0127. And if you're not sure where the 7,200 came from, we knew that we had 80 samples taken. Okay, so we had our 80 values, and that of those 80 values, the mean was 90. And so if we multiply those two, that's where the 7,200 comes from. All right, now for part B, it's asking us to find the sum of x when z is 1.5. So that's 1.5 standard deviations above the mean. And so to do this, we just need to know that our mean, when we look at that bell curve, the mean of the sums was 7,200. And that just comes from the number of the sample times mu. So that was our 80 times 90. Okay. So as we look at that, we want to know what is 1.5 standard deviations, or a z-score of 1.5, above the mean. So we're going to do the mean. We have to start here, and we're going 1.5 above the mean. So we're going to do 1.5 times the standard deviation, which in this case is the square root of n times the standard deviation. So that's the square root of 80 times the standard deviation of 15. And we have to add that to the 7,200. And that gives us the value of 7,401.2 is the value that is 1.5 standard deviations above the mean. All right, one of the hardest parts about this, the central limit theorem, is knowing when you're supposed to use the central limit theorem. So this is when you use it. If you're being asked to find the probability of the mean, or if you're asked to find the probability of the sum or total. And then as well, if you're trying to find the percentiles for the means and sums. If you're being asked to do one of those three things, so the probability of the mean, the probability of the sum or total, or percentiles for means and sums, this is when you use the central limit theorem. All right, that kind of wraps it up for the central limit theorem for stats. And please give us some feedback. Let us know how these are helping you. If we can add a little bit more to it, we want to, but we're trying to keep it as efficient and succinct as possible. So we hope that you're doing well, and we'll catch you on the next one.